just wanted to do a quick video on Slater's rules, but specifically Slater's rules when we've got d orbitals in our elements, because sometimes that can cause us to have to think about things a little bit differently. So I thought I'd walk through a couple of examples and really explain to you how to handle the d orbitals. And also what I'm going to talk about today would explain f orbitals as well, but we don't often get that far talking about normal, everyday run-of-the-mill chemistry. So here's how I would approach a problem in terms of Slater's rules with d orbitals. Let's do a couple of different cases. Let's first imagine that we are interested in calculating the effective nuclear charge. So ZEFF, let's just indicate that there. And suppose we are interested in calculating that effective nuclear charge for two different cases. One, let's think about one of the electrons in our outermost orbital, right? So I've taken the liberty of talking about bromine, and bromine is element 35 in the periodic table, so we know it's got 35 protons, which is its actual nuclear charge, and I've written out its electron configuration, something that we've studied in depth in this class so far. Now, our outermost, or our highest principal quantum number here is 4, obviously, and I've written these orbitals out in their energetic ordering, right? So the order I would have arrived at them walking through the periodic table. And so let's suppose that we're choosing one of these outermost electrons, right, in this 4 group here. So we could consider that. So what is the effective nuclear charge for an electron in the 4s orbital, right? So that's out there in that outermost zone. And then after that, let's also consider what would be the effective nuclear charge for an electron in the 3d orbital. Remembering that we can calculate the effective nuclear charge for any electron in any orbital. We usually think about the outermost electrons because they're the ones that dictate most of the chemistry, as we discussed in the last lecture, but it doesn't mean that we can't calculate an effective nuclear charge for any electron. The only thing we really need to know is what is the value of the shielding constant. In other words, how much is that particular electron shielded by the nucleus? So that's the thing we'll be concerned with calculating today. And we already know the rules somewhat for how to do that. So let's jump into this example right away. The first thing that I like to do when I'm thinking about a Slater's rules type calculation is I like to reorder all of my orbitals here in terms of those spatial zones we talked about earlier. And this is the first case where I really need to think about D's differently. So let's write that now. As I would indicate these in terms of their spatial zones, obviously we would keep our 1s by itself, so to speak. So I'm just going to put that in parenthesis just to remind us that that's one spatial zone. And in this case, of course, it's the closest spatial zone to the nucleus. And then, of course, we'll continue on in the same way we've done in the past. So there's the n=2 spatial zone. And then here is where we start to run into differences where I'm really going to account for d orbitals. So what I'm going to do here is I'm going to write my principal quantum number 3 next, but I'm actually going to separate the d's, okay? So this is something we didn't run into last class. I'm going to put the d's in their own spatial zone, okay? And there's a good reason for that, and we'll talk about that in a moment. And then finally, of course, we have our n=4 spatial zone, which is the farthest away from our nucleus and therefore goes out there on the end. And so now I've rewritten my electron configuration essentially in terms of distance from the nucleus, if you will. And the only question is, why would I write my d's differently? Why would I indicate them there and not with the group of 3? Well, really the reason here is, we have to first recall that Slater's rules are really just an approximation. These are really just some basic hand-waving type rules that we can start to rationalize the behavior of atoms. So calculating, how much an electron would be shielded out from the nucleus would require really in-depth quantum mechanical calculations, and Slater's rules is just sort of a quick approximation at that. And so there's always going to be a few sort of edge cases that have to be considered in a way that's maybe a little bit different than what would be typical rules. But it doesn't mean that there isn't a simple explanation for this. And fundamentally, the explanation for this comes from the shape of the d orbitals. let's not forget what the shape of the d orbitals looked like. They had that sort of cloverleaf pattern, right? And the key thing to understand about this cloverleaf pattern was that there were two nodes, or two nodal planes, through this orbital. In other words, there were regions of space defined by these nodes where electrons are not allowed to go at all, right? They're just not allowed to go there. And so that has serious implications on those electrons' ability to shield out other electrons or be shielded by the nucleus from other electrons, right? So imagine something like the s orbital, for example. So the 3s orbital. So let me just sort of draw it at the same sort of scale. The 3s orbital doesn't have any of these nodal planes. Doesn't mean it doesn't have nodes, but it doesn't have these regions, cutting through the nucleus that I'm not allowed to go. It doesn't have those at all. So the electrons that are in the 3s orbital are really able to go wherever they want in terms of around the nucleus. And so the electrons in the 3 orbital, recalling that these orbitals will be, of course, superimposed on one another, electrons in the 3s orbital are able to go into these exclusion zones, into these places where the electrons in the ds are not allowed to go. And so the ds don't effectively block out other electrons, not like s electrons do. As well, the s electrons are able to get closer to the nucleus, more close to the nucleus than the ds are able to get to, because the ds are more restricted in terms of the spatial, range that they're able to travel through. So for that reason, we lump Ds separately in this schematic diagram here. And there's another way that we take into account Ds and treat them a little bit differently too, but I'll get to that in a moment. So we've specified our zones here. The first difference that we're doing to take into account d electrons is by grouping them by themselves. And really, if we were doing Fs, F orbitals would be grouped by themselves as well. But that's really the only change that we have to make. So now that we have these spatial zones, we can do a Slater's rules type calculation, recalling that the value for my shielding constant, S, is 0.35 for electrons that are with me in my same zone, 0.85 when we go into one zone closer, and then 1 for every other zone closer than that. So in the case of a 4s electron, I'm in this zone. So I look and I say, well, I've got a total of 7 electrons. Therefore, there must be 6 others. So S is equal to 6 others that all get a value of 0.35. So 6 others that shield me about 35% of the time. And then when I go one spatial zone in, remember that the value that these electrons get is 0.85. So in this case, I've got obviously 10 electrons in the 3d orbital, all shielding me with a value of 0.85. And then subsequent to that, I consider every other electron inside. Doesn't matter how far in I need to go. Everything else is so much closer to the nucleus than I am out here that they all shield me completely. So there's 8 electrons here, another 8 here, and 2 here for a total of 18. So I will indicate that here I've got 18 electrons that are all shielding me completely. And what this equates to, if I do the math here, 6 times 0.35 and 10 times 0.85, 18 times 1, I will get a grand total of 28.60. Okay, so that's my shielding value, particularly for a 4s electron. Okay, so now if I want to calculate my effective nuclear charge, which is what I do want to do, my effective nuclear charge is going to be equal to my actual nuclear charge, which remember is 35. And this is 35 exactly. There'd be as many decimal places here as I wanted. There's no significant figures here that I have to worry about. And I take away my shielding constant, which is 28.60 in this case. And so my effective nuclear charge then becomes 6.40. And that's my final answer in this particular case. So that's how we work with Ds in that context. Now, it doesn't mean we're totally done yet, because there is the scenario of what happens if it's actually a d electron that I want to calculate the effective nuclear charge for. So same diagram here, or same electron configuration, but now suppose I'm an electron in this spatial zone. What is the effective nuclear charge that I see through all of these different electrons in closer zones than me. And this is just the one other case that we have to think about in a bit of a special way. And it's exactly for the same reason. Recalling again that these d orbitals have that clover leaf pattern. They are more restricted in terms of their spatial range. They can't quite get as close to the nucleus because of all those restrictions. And what happens is all orbitals inside of a d shield it effectively completely. And so the way we handle this is we do the same sort of things, but we skip the 0.85. We say that orbitals that are inside of a d, orbitals that are closer than a d, like these s's and p's, don't have those same kinds of restrictions as a d set of orbitals do, and so they are much more effective at blocking out those d orbitals. And so we go straight to the value of 1 in this case. So let's try that. Our S, or our shielding constant, is however many electrons are with me in my own spatial zone. So of course there's 10 electrons here. If I'm one of those, if I'm imagining that I'm one of these 10, then that means there's 9 others. And so I have 9 other electrons that are all going to shield me at a value of about 35%. So I get about 0.35 shielding constant for each other electron here. And now I've got 8 electrons here in this next spatial zone, but again, remember that the trick here with dealing with Ds is that we are going to jump straight to the 100% shielding value because Ds are so ineffective at allowing their electrons to get close to the nucleus. And again, that's because of their nodal structure. The more nodes you have, the more ineffective you are at getting to that nucleus. So that means I don't just have these 8, I actually have all 18. All of these electrons I'm going to consider as having that perfect 1.0 shielding factor, right? So that's what I'm going to do. So I don't do the 0.85, and that's the key difference here. Now, adding those together, 9 times 0.35 plus 18 should give you 21.15. And so our effective nuclear charge for this particular case is going to, again, be equal to the actual nuclear charge, 35, minus this shielding constant, which is 21.15, and our final answer here becomes 13.85. Okay, and that is, of course, a much larger number than the 6.4, but that's because we're talking about electrons that are significantly closer to the nucleus and have significantly less electrons shielding them out. So of course, our d electrons are more tightly bound to the nucleus here than our outer 4s are. But anyway, that's how you deal with d orbitals. And that will help you certainly in some of the practice problems and dealing with any curveballs that you might see.